One of the ways in which a scanning microscope helps is that it is very easy to combine the microscopy with X-ray spectroscopy. And X-ray spectroscopy is quite rich in terms of providing information about the local chemical environment. And so, for instance, in the spectrum you see on the right-hand side here, there is a solid line which shows the absorption spectrum near the carbon K absorption edge of acrylonitrile, and in dashed you see the absorption spectrum of polypropylene. On the left-hand side you see 4 panels of a mixture of these two polymers on a scale where you can see the 5-micron scale bar. Image A was taken at the high peak of acrylonitrile at around 285 electron volts, and you can easily see that this material is shown black on the image. On the other hand, panel D was taken at the point where around 288 electron volts polypropylene absorbs more than acrylonitrile. And so you can see the polypropylene black while the acrylonitrile is in gray. And so you can easily identify what is where. In the subsequent years, Chris Jacobson and collaborators have developed the software to automatically take a whole series of images at closely spaced energies and then align these images, and thereby making it possible to pick any point on the image and acquire a spectrum there, thereby identifying the local chemical environment anywhere, even if that environment is quite complicated. So let me just jump to the current situation where X-ray microscopes are sprouting at all synchrotron radiation sources. At the Advanced Light Source, where I'm currently working, there are 5 X-ray microscopes in operation, and they are heavily oversubscribed for a variety of applications. But to go a little bit less provincial, I should point out that, for instance, at the Advanced Photon Source at Argonne National Laboratory, there are also several microscopes, and on Thursday, Jörg Maser is going to describe in detail the APS nanoprobe. You will see that on several of my transparencies, I will put pointers to future talks during this meeting so that you know where you can find more information. Now, one of the exciting things that is happening in X-ray microscopy is that one doesn't just take simple snapshots in 2 dimensions, but one goes to 3-dimensional imaging. I already mentioned spectral microscopy, where the 3rd dimension is the X-ray energy, and I will show some examples of that as well. But the 3rd dimension can be other things as well. Naturally, the 3rd dimension can be spatial dimension, where you are doing tomography. You rotate the sample and acquire a set of images from which you determine the 3-dimensional structure. And Gert Schneider is going to talk about that on Thursday. Or you can just repeat the picture at rapid sequences in order to see time-dependent phenomena. And Eve Ackerman is going to talk about that this afternoon. Whenever you are doing imaging using ionizing radiation, you always have to worry about radiation damage and keep that in mind. So for instance, when you are looking at time dependence, you have to make sure that what you are looking at is not the consequence of radiation damage, unless that's what you are interested in. So here is an example of spectral microscopy. This is work that was done in Adam Hitchcock's group, but the data was collected at the Advanced Light Source. And this is an ecological example where you look at sludge. This is river biofilm cultured in river water spiked with nickel chloride. And what you can do is by going through the spectra near the nickel absorption edge, the manganese absorption edge, and the iron absorption edge, you can identify and locate the various metals that are distributed in this sample. And in the case of manganese, because the spectra have different peaks for the different oxidation states of manganese, you can separately identify the different manganese chemistry by looking for the peaks in these absorption spectra. Going to higher energies where what you detect is fluorescence, which is characteristic of different elements, you can map the different elemental distributions in a sample, and this is work that was done at the Advanced Photon Source at Argonne National Laboratory looking at trace metals in plankton. There has been the suggestion that you can capture a lot of carbon dioxide by seeding the oceans with iron, because the plankton would then bloom and absorb a lot of the atmospheric CO2. So the question was, where does iron go in the plankton? And what you find is, if you look at the iron map, it has concentration which resembles the epifluorescence, which shows the location of the chloroplasts. So the suggestion is that iron is deposited or absorbed at or near the chloroplast in the plankton. Now, the Stanford synchrotron radiation light source got into the act relatively recently with the acquisition of a tomographic microscope from the company X-Radia. And they are using a 54-pole Wiggler in order to illuminate it. And they get something around 30 to 40 nanometers three-dimensional resolution in either phase or amplitude contrast in the relatively hard X-ray range from 5 to 14 kilovolts. And so in the left, you see a three-dimensional reconstruction of a lacuna, which is the cavity that houses bone cells in a mouse bone. What you see in the center is mercury in the root of cordgrass. There are yellow microbes and blue biofilm, all brought out from this three-dimensional reconstruction of the image. In each case, these images are about a field of 20 microns. The third picture, which should rotate in principle, but it doesn't, is nanowires that were imaged. But I want to mention that synchrotron light sources are not absolutely necessary for doing X-ray microscopy. In fact, at this conference, you are going to hear a lot about tabletop laser sources, including tomorrow by Henry Captain and Margaret Murnane, and also by Carmen Menoni, who was just celebrated this morning for having become a fellow of the American Physical Society. Furthermore, on Thursday, you will hear from Hans Hertz, who will describe a microscope that is based on an X-ray source where you have a liquid jet and you hit the droplets in the liquid jets with an intense laser. And finally, you will also hear from Wenbing Yun from X-Radia, who will describe the commercial tomographic microscope, of which an example I have shown you is operating at SSRL.